Every year, thousands of people gather here to enjoy the sport of in San Juan Bautista, California. The base of this bank, or scarp, marks the point where two huge portions of the Earth's are colliding, grinding past each other with a force that reduces hard rock to powder, with a power that can create mountains and trigger violent tremors built over hundreds of miles of countryside. The same forces are at work 125 kilometers north, near the metropolitan area of San Francisco. In 1906, this city was devastated by one of the greatest earthquakes in California history. More than 700 people lost their lives. For modern San Francisco, this disaster had one positive effect. It prompted study into the origins of earthquakes. Soon after the 1906 earthquake, it became evident that a single geological feature dominated California's long history of seismic activity. The feature was named after the lake that it forms just south of San Francisco. Today, it is known as the San Andreas Fault. Near San Francisco, urbanization has plowed over the fault and nearly obliterated its trace. But the fault becomes clearly visible in a radar image of the San Francisco Bay Area. Muscle Rock, where the fault dips into the sea. San Andreas Lake. The Central Fault region, where deep, straight valleys mark the fault's path. To the naked eye, the San Andreas Fault is most evident on the barren flatland of Central California's Carrizo Plain. Here, where there is scarcely a trace of civilization, the fault is visible as a thin, well-defined line of deformation, crossed by an occasional dry stream gully. In some places, the fault is traced by the foot of a gently sloping hill, or by a shallow depression in the landscape. In others, it is more obscure, its presence marked only by a primitive road. More dominant features can be seen farther south on the Carrizo Plain, where a few desolate farmhouses dot the land. The fault appears as a thin valley that cuts across the general slope of the plain. Where the terrain is steep, the centuries have etched their mark into the land with deep, eroded channels that descend from the vicinity of the fault line. Altogether, the San Andreas Fault slices through some 1,100 kilometers of California countryside. From Mexico, north through the San Francisco Bay Area, and on into the sea. In many places, it is not a single fracture, but a complex zone of branches called the San Andreas Fault System. On the southern portion of the fault system, east of the Salton Sea, rocks have been squeezed and fractured by pressure in the fault zone. As evidence of its powerful motion, the fault has left slick, highly polished rock surfaces. Evidence of this sort is often found where road construction has torn away part of the Earth's surface. Near the town of Gorman, a road cut exposes a mass of granite. Granite is often used for building. Normally, it is a strong, durable rock. But in the fault zone, this granite has been crushed almost to a powder. The softening is the result of millions of years of grinding action. Farther south in the fault zone, A highway passes through terrain that has been forced upward by pressure around the fault. Where the road intersects the fault zone, rock on the face of the road cut is contorted and twisted by the compression of two huge sections of earth squeezing together. Changes like this take place very slowly. The awesome forces that come into play are rarely experienced directly by man. But proof of motion along the fault is here, in the geologic record of the land. One of the most dramatic examples of this proof can be found in the Carrizo Plain, where the dry gullies of drainage creeks descend to the fault line. These streams do not flow in a straight line. At the fault, they veer sharply to the north. The offset of this stream is the result of motion along the fault. This model shows how the offset was produced. Land on the western side of the fault has been moving slowly northward with relation to the eastern side. Where the stream crossed the fault trace, this horizontal motion diverted the flow. Further motion completely interrupted the stream's path. Eventually, the waters of the stream eroded a new path into the land. But again, the new stream was offset by movement along the fault. Today, the stream is displaced about 20 meters to the right where it crosses the fault line. This offset is probably the result of several hundred years of fault motion. In geologic terms, several hundred years is not a very long time. Much greater displacements, involving much longer periods of time, have occurred along the San Andreas Fault. Over millions of years, this movement has been sufficient to displace huge blocks of earth. In this creek bed, two different types of rock lie side by side. The rock on the left is about 3 million years old. The rock on the right, a few thousand years old. The fault is evident between the sections, where a soft, pliable substance called fault gouge has been formed by the Earth's relentless squeezing and grinding action. Matching of rocks on opposite sides of the fault zone gives an indication of how much the Earth has moved and how long it has been moving. A sample of an unusual and easily recognizable type of rock is selected from the western side of the fault zone in central California's Fraser Mountains. In the desert of Southern California, an outcrop of identical rock is found in the Orocopia Mountains on the eastern side of the fault. This suggests that movement along the fault has separated one massive rock into two, probably over a period of about 20 million years. The separation is shown by the points marked A on this map. The matching rocks are about 300 kilometers apart. Geologists have mapped many distinctive rocks that seem to have been separated by fault motion. The oldest rocks are the farthest apart. The motion that occurs along the fault takes two distinct forms. One is the very slow, nearly continuous movement that geologists call creep. This fence has been offset by creep. The motion is slow, but persistent. Normally, creep can be observed only through its effects. In Hollister, California, the Almaden Winery sits directly atop an active branch of the fault zone. Inside one of the winery warehouses, reinforced concrete walls and floors are slowly being pulled apart by creep movement along the fault. This simple model shows how the displacement takes place. The slow movement of creep can be measured. Here, the Earth is moving at an average of about 13 millimeters a year. The other form of fault movement is sudden and sometimes violent, the earthquake. Severe earthquakes contort and destroy man-made objects of all descriptions. In California, they often originate along one of the branch fractures that make up the San Andreas Fault system. The sudden power of most California earthquakes is released less than 12 kilometers below the surface of the Earth. The shock waves that radiate from their centers can damage buildings at distances of 150 kilometers. The amount of energy released varies widely. The energy of this earthquake was less than 1% of that released near San Francisco in 1906. It is obvious that earthquakes are closely related to movements of the Earth's crust. Geologists believe that the San Andreas Fault may be the border between two huge portions of the Earth's crust called plates. The Pacific Plate, which includes the western sliver of California, is moving slowly northwestward with relation to the North American plate. This model will show how the plates move. The white lines are for reference. Plate motion in the model causes the buildup of strain. The strain is released in sudden slips. In the same way, strain builds along the San Andreas Fault. Generally, friction between plates causes the locking of rocks along the fault. When the locking rocks give way, the strain built up over long periods of time is released in a matter of seconds. The result is an earthquake. To learn more about when and where earthquakes might occur, geologists study many kinds of movement along the San Andreas Fault. At present, few geological phenomena are analyzed by more scientists or monitored by more sophisticated equipment. Near Bear Valley, south of Hollister, one of hundreds of tilt meters measures the slope of land that is warped by elastic strain near the fault zone. Even the slightest change is recorded by the meter. It is so sensitive that it reacts to the earth wave created by the footsteps of an approaching man. The fault is also studied with laser beams that measure horizontal movement over long distances. A narrow, intense beam of light is aimed from one side of the fault to a reflector 10 kilometers away on the other side. Meanwhile, a helicopter flies close to the line of sight to collect atmospheric data that could affect the readings. The travel time of the light is recorded and corrected for the atmospheric distortion measured from the helicopter. Any motion along the fault is detected as a change in the shape of a laser triangle. Minute fault movements can also be measured directly with sensitive creep meters. This pit is the terminal point of an underground wire that stretches diagonally across the fault. If there is any movement, the wire is pulled. The displacement is measured and recorded. Earthquakes, too, are constantly recorded. Hundreds of minor tremors occur along the fault every year, most of them so slight that they can be detected only by very sensitive instruments. Seismometers on the fault zone measure these tremors and relay the information to data collecting stations by radio. This information, translated to seismograms, provides a continuous picture of tremor activity in the fault zone. Some types of earthquake research can be conducted under controlled laboratory conditions. In this experiment, a sample of rock is subjected to shear stress. The object is to duplicate the kind of locking and slipping behavior that is characteristic of rock deep in the San Andreas Fault zone. Through electronic sensors, tremors in the rock sample are measured. They result in seismograms that closely resemble those produced by real earthquakes. This experiment can be repeated while varying the pressure, temperature, and water content of the rock. Geologists can thus learn if any of these factors are important in determining when and where earthquake activity may occur. At the National Center for Earthquake Research in Menlo Park, California, data is received from hundreds of instruments all along the fault system. Statistics on tilt, strain, creep, and tremor activity are collected and stored. Current conditions are monitored, and data is fed into computers. The computers combine data compiled over many years and translate it into visual form. Month by month, tremor by tremor, a computer provides a graphic readout of seismic activity in the San Francisco Bay Area. A close look at this readout shows very little tremor activity in the northern portion of the fault system. The fault appears to be locked. Elastic strain is probably building up. Geologists estimate that the strain in the fault's northern reaches is already approaching the level that preceded the devastating earthquake of 1906. If that earthquake were to be repeated today, its tragedy would be increased manyfold in modern California. Geologists and engineers have tried to estimate the effects of such an earthquake. In one estimate, property damage exceeds $24 billion. More than 100 bridges and freeway overpasses collapse. 10,000 residents of the San Francisco Bay Area are killed. The San Francisco Bay Area is today the home of more than 3 million people. Another 7 million are centered around metropolitan Los Angeles. It has been estimated that by the end of the century, 1/7 of the United States population will live in the state of California. Most of these people will be living in the shadow of the San Andreas Fault. Some geologists say that California's next major earthquake could come tomorrow. Others say it won't come for 100 years. But all agree that it is coming. The question of when and where the next major earthquake will strike is of great importance to the people of California. But the San Andreas Fault and the motion along it are only small parts of a much larger story. Somewhere, deep within the planet, an unknown force is causing huge sections of the crust to move, gradually rearranging the surface of the Earth. What is the nature of this force? Where does it originate? And what effect will it have on the geography of the Earth for millions of years of geologic time?